Hi, this is Kevin. Welcome to my lecture for Chapter 6 from the Zelle 3rd edition Python book. And Chapter 6 is about defining functions. As usual, I'm going to leave the objectives for you to read on your own. So, what's the function of functions? So far, we've seen 4 different types of functions. Our programs comprise a single function called main. Okay, and main is it's an arbitrary name. It's a traditional name, so it's a good practice kind of name, but it has no magic to Python. And in the early part of our course, before we get here to Chapter 6, we're simply putting all of our code into main. Okay? What we're going to find when we're done with Chapter 6 is that we're going to, for larger programs, we're going to break out portions of the code and allocate them to their own individual functions. And then main is going to orchestrate them, and then it's going to be the main function. So the choice of main for that function, the name, seems more appropriate when you see what it really does in a larger and or more complex Python program. Then we've got the built-in function. We've got print for printing. We've got abs in order to calculate the absolute value of a number. We have functions from the standard libraries, okay, like the square root function from the math library. And the last of these, the getX, this is something that the author wrote and introduced in Chapter 4, and we don't cover Chapter 4, so we're not going to talk about that. Having similar or identical code in more than one place has some drawbacks. Issue 1, writing the same code twice or more. So you have to write it more than once. Issue 2, the same code must be maintained in 2 separate places. That's true. So you have to write it. Well, you have to write it more than once. You have to test it more than once. You have to maintain it more than once. Okay, so that's not something that we typically want to do. So we can use function to reduce code duplication and to make programs more easily understood, read, and maintained. Okay? So there's one term that isn't included in the Zelle text that's more recent. More recent in terms of it's kind of favored by the young guys and the young gals, both guys and gals tend to favor this. And there's an acronym, DRY, D-R-Y, and it stands for Don't Repeat Yourself. So that's a way to remind yourself to get rid of duplicate code by creating common functions that can be called by in more than one place in your program. Okay? Let's get the next slide here. A function is like a subprogram, a small program inside of a program. The basic idea is we write a sequence of statements and give that sequence a name. We can then execute this sequence at any time by referring to the name. The part of the program that creates the function is called a function definition. And we've already seen that. We've been using that syntax when we define the main function. When the function is used in a program, we say that the definition is called. So we call the function or we invoke the function. Okay, so now we're going to introduce a program, and it's one from the text, and it's called happy. Okay, and so I'm going to bring over PyCharm so you can see it. Okay, and here's the original version from the text, and it's got the problem of maybe inappropriate contents and oh, it doesn't have enough blank lines and the functions are in the wrong order and all those kinds of things. So I've created a refactored version, happy refactored, okay? And it has a doc string up at the top, which is standard. Sing happy birthday to Fred, Lucy, and Elmer. Okay, so when we're done messing around with the program, this is the program that we have. Okay, and it has a main, and from main we call a method called sing, and we call it 3 times, and each time we pass in a different parameter. Okay, so if we look at sing, it receives the parameter, okay, and then it prints happy birthday to you, happy birthday to you. How does it do that? Well, it does it by calling another level of function called happy that only prints happy birthday to you, okay, and then its main job is to print the personalized verse in which it says happy birthday dear person name. Okay, so then we have a period at the end, and then it goes on, happy birthday to you. Okay, so this is how this looks. Okay, we haven't explained all the parts yet, but if we run it, run happy refactored, we're going to get happy birthday, you know, the lyrics sung to Fred and then to Lucy and then to Elmer, and the upcoming slides are going to sort of explain how that happens. Okay, it's all based upon this program, and my refactored version is the cleaned up one. All right, so here's an example of an early version of the program that sings happy birthday only to Fred. Okay, so it's not so complex as the one that we wind up with. Okay, so what's good about this? Well, what's good about this is it's very simple. What's not so good about this compared to our final version? Well, it sings a happy birthday to Fred, and it's not easily expanded to singing happy birthday to additional people without copy pasting. Okay, so let's go on, and we'll keep improving it. Okay. And in addition, the author is concerned that we have some duplicated code. So every time we sing happy birthday to you, we're typing it in all over again. And of course, we could make a typo, we could make a mistake. And it's probably not likely. This is always a problem with illustrating these principles with printed lyrics, right? Because in real code, as time goes on, the requirements in the real world change. Okay. But this isn't true of traditional songs and poems. So, are the lyrics to Happy Birthday to You going to change over time? Well, not likely. Okay. We may pronounce happy or birthday slightly differently 100 years from now, but they're probably not going to change. But the cost of maintaining all these lines of code that print happy birthday over time isn't really that high in the real world. But if this were real code, that it's something else over and over again for our organization in whatever activity that it does. Chances are that over time that activity would change subtly on a day-to-day basis, but on a year-to-year and decade-to-decade kind of basis, it would definitely change. Okay, so not only would we have to write it more than once and test it more than once, but we would have to maintain it more than once. Whereas the maintenance issue on Happy Birthday is kind of hard to sell. But that's okay. We want you to not worry about that for now. So we improve this by let's see. He created a function called sing_fred that's going to have the main logic, and he put a function called happy which prints happy birthday to you, and he put happy before the code that calls this, and this is not a problem for Python. Okay, as long as you've defined all the function before you call the main function at the very end, it doesn't really matter to Python what order they're in. But typical good practice is to put them in kind of hierarchical order. So put the topmost one that's at the top of the calling hierarchy at the top. So if I were to do this, I would have put sing_fred before happy. Okay, so he did this and he got out some of the duplicate code. Okay, he doesn't have to worry that he's typing in or testing or theoretically would have to maintain this happy birthday to you over and over again. Okay. So now, what about if we want to sing happy birthday to Lucy? Okay. Maybe we've got 3 people in our work group whose birthday it is this week or this month. I've worked at places where instead of having a birthday celebration throughout the month, we have one big birthday at the end of the month or the beginning of the month, right? So maybe during the month, Fred and Lucy and Elmer all have a birthday. Now we start to see the drawback of having to custom craft this for every person. Okay, so we need a custom line for Lucy, and we created a function for sing Lucy as well. Okay, and so now he's got a main. Okay, and I'm sorry, he's showing us that last because theoretically that's the last thing he wrote. And when I say he, I mean the author, John Zelle. So he's got a call to sing_fred, a print that prints a blank line, and a call to sing Lucy. And so now you get the lyrics to Happy Birthday for Fred and Happy Birthday for Lucy. And if you look back, you can see that this, because Sing Lucy and Sing Fred look suspiciously the same, you can see that we're repeating a code. So it turns out there's an opportunity here, and the opportunity is in passing parameters. And I think I showed you in the final version that that's how we solve the problem. Okay, so this is the combination of Sing, Fred, and Lucy. Okay. So if we use a parameter, okay, we can further combine the code. And that's where we go. Okay. So now, instead of having a sing Fred function and a sing Lucy function, we have a sing function, and it's expecting to receive a parameter that it's calling person. Okay. And the parameter names that appear on this function header, this definition of the function, these are called formal parameters. Okay. So this function uses a parameter named person. A parameter is a variable that is initialized when the function is called. Okay, so that's how we use person. We use it in here. We use it to personalize the happy birthday, dear blah blah text. So now, if we call sing Fred, we get the appropriate output. And yeah, we could we could call it sing passing Fred, print a blank line, sing passing Lucy, okay, and we get happy birthday for Fred, happy birthday for Lucy. Now, this is how we call or invoke a function. We just type in the name, okay? If it doesn't take any parameters, we just have empty parens. It just would be sing paren paren. And we'll see in a minute that's what we do for happy. I think we may have already seen that, okay? If we're going to pass a parameter, okay, we put the parameter inside the parens, okay? And it can be either a literal, like Fred as a literal string, or 1 or 2 or 3.5 are literal number values. It can be either a literal or it can be a variable name, okay? And we're going to find out later that if we need to pass more than one, we simply separate them by commas. So at least, the first skill that we learn is passing a single parameter, and then in a while we'll be passing 2 or 3 or perhaps 4. Okay. Now, these parameter values that are in the calling code are called actual parameters. Okay. Now, in some other computer languages, they call the parameters that appear on the calling code, they call them arguments, and the parameters that appear on the call code, they call them parameters. But in Python, the formal language is the parameter that appears on the calling code is an actual parameter, and if we back up, it's a parameter that appears in the function header. I'm sorry, in the called code. So the call code is called the formal parameter, and the calling code is called the actual parameter. Those are the proper names in the Python world. But you may hear people say, I'm going to call it with certain arguments. That's kind of loose speaking for I'm going to call a function with these actual parameters. Okay. So here's our new main program. Okay. Sing Fred, sing Lucy, and we get those results. Okay. So again, I'm going to show you the the finished version in PyCharm, right? And this one syncs to 3 people, and this is just what the program did when I found it in the collection of programs that came with this chapter. So main is the function that orchestrates the action. There's a call to sing with the actual parameter Fred, a print a blank line, sing Lucy, print a blank line, sing Elmer. Okay, and then sing calls happy 3 times. And as you can see, since there's no parameter, since happy isn't expecting to get a parameter value, well, the parens in the call to happy are just empty. Okay, and happy just prints happy birthday to you. And then finally, sing does its custom action, happy birthday, dear person. And again, this formal parameter name is used like a variable inside of the sing function. Okay, and that's how it works. So when we run this, we get happy birthday to you customized for 3 people, 3 different individuals. Okay, and so we've done, we've eliminated duplicate code in a couple of different ways. Using that dry or don't repeat yourself principle. And this is the first time that we've really taken advantage of the power of parameterizing a function such that we can take behavior that the program is supposed to have that's a little different each time we call it and customize it. So as a result, the behavior that we need from the function doesn't have to be exactly the same every time if we can pass in parameters that can be used to customize the behavior. We didn't cover this future value code, so we're not going to talk about it. So that takes us on to functions and parameters, the details. So I'm not going to talk about the first point because that has to do with that drawbar, which all goes back to chapter 4. But one important concept I am going to talk about is the scope of a variable. It refers to the places in a program that a given variable can be referenced. Okay, so we say that it's visible there. Okay, so each function is its own little sub program. The variables used inside of a function are local to that function. So that name is only known inside that function, even if they happen to have the same variable names that appear inside of another function. One kind of fancy computer sciencey way to say this is we would say each function has its own namespace. Okay, names have to be unique within the function. The only way for a function to see a variable from another function is for that variable to be passed as a parameter. So once we get into functions, once we get into programs that are made up of multiple functions, the best practice is to define every variable inside of one function or other. And the only way for them to share values is by passing a parameter, and we'll eventually see that called functions can also return a value. Okay, they can't see inside each other. So now we're back to that stuff from chapter 4. Okay. A function definition looks like this. Well, it doesn't really look like this. This is a syntax, a diagram for a function definition. So we've got the def keyword, a space, then we've got the name of the function, no space, parens, okay, a list of formal parameters. Okay, if there are no formal parameters, the parens are just empty, and then it ends with a colon. And then the body of the function is indented, one indent uh, under that line up here, which is appropriately called the function header. The name of the function must be a proper Python identifier, normal snake case Python names. Um, the formal parameters is a possibly empty list of variable names. Formal parameters, like all variables used in a function, are only accessible in the body of the function. Variables with identical names elsewhere in the program are distinct from the formal parameters and the variables inside of the function body. So if the names used in various functions to refer to data either as a variable or as a formal parameter name, if they're the same from function to function, it's just incidental, okay? They can't be seen from function to function. They're insulated from each other. A function is called by using its name, followed by a list of actual parameters or arguments. So again, even though these things are called in the, in the Python specification, even though they're called actual parameters, the calling values are sometimes referred to as arguments. That's because what we call them in other programming languages. So we have the name of the function, a paren, no space in between, and then the actual parameters. Okay, if there are more than one, they're separated by comma spaces. If there are none, well, the parens are empty. When Python comes to a function call, it initiates a four-step process. And one of the things I really like about this Zelle book is I think he describes this in a really nice way. So I really like this next part. So the calling program suspends execution at the point of the call. Okay. The formal parameters of the function get assigned the values supplied by the actual parameters in the call. Okay. They get assigned the values. The body of the function is executed, and then control returns to the point just after where the function was called in the calling code, and then we go through the sequence again. So the default behavior of code is it just executes in sequence one after the other. If one of the statements in a sequence is a call, well, that interrupts the sequence to do these things. And then when we come back, control returns to the point just after the call in the calling code, and then we start doing the sequence again. So let's trace through the following code. So we have a call to sing with the parameter, with the actual parameter Fred, a call to print, a call to sing with the actual parameter Lucy. When Python gets to sing Fred, execution of main is temporarily suspended. Python looks up the definition of sing and sees that has one formal parameter, person. The formal parameter is assigned the value of the actual parameter. It's as if the following statement had been executed. So now person gets associated with the value Fred. Okay, that makes sense. So this is a little bit more graphical way to say the same thing. So here's the code from main. So we have a sing Fred, okay, and this sequential execution of the statements in main is interrupted when it gets to the call, okay. Uh, so then we go over and we begin to execute sing. The first thing that happens is that this Fred value is associated with the formal parameter person, okay? And then we call happy, okay, and happy, and then we do happy birthday, dear person, okay? But I'm getting ahead of the slides. So note that right here, the variable person has just been initialized. And I want to clean that up and say that uh, person is an actual parameter. They behave like variables in the body of functions, but it's an actual parameter. No, I'm sorry. It's a formal parameter. My bad. Okay. So it's a parameter, not a variable. Okay. Once you're in the code, once you're in the body of the code for a function, the distinction between these parameters, these formal parameters, which were created in the header, and any other variables that are created in the body of the function, it's a very fine distinction. At this point, Python begins executing the body of the function sing. The first statement is another function call to happy. What's next? Python suspends the execution of sing and transfers control to happy. Happy consists of a single print, which is executed, and control returns to where it left off in sing. So we were in the beginning of sing, okay, and we assigned the value Fred to the formal parameter person, and now the first thing that we do when we execute the body is we have a call to happy, and we interrupt here, and we go down and we execute happy. We don't have to set the value of any formal parameters because there are none. So we simply execute the print of happy birthday to you, and we come back. Okay, so this can go down level after level after level. I think there is a limit, but it's really high. It wouldn't be anything. You could go down at least maybe 256 or 512 levels or 1024. It's some power of two probably, but it's very, very, very high if there's a limit. Okay, not something for us to worry about. A program that we would write would never get that deep. So execution continues in this way with two more trips to happy. That's happy and happy. When Python gets to the end of sing, control returns to main and continues following the function call. So right over here it goes to the print. So the default behavior of Python code, and really code in all these computer languages, is sequence. Okay, when nothing else is happening, well, then we go down and we execute the next thing in the sequence. Notice that the person variable in sing has disappeared. Well, this is interesting to see. Let's go back. Okay, so we we have the call to sing with Fred, okay, and the person gets associated with Fred, okay. What happens when we come back and get ready to do print? Okay, uh, that Fred has just gone away. Okay. One of the interesting things about these called functions is that they release all their data storage when they're done. They don't remember values from execution to execution. Okay. The memory occupied by local function variables is reclaimed when the function exits. Local variables do not retain any values from one function execution to the next. Now that would seem maybe inconvenient. You might think of a function where you'd want to remember values, and there are kind of architectural things to do to make sure you have a place to keep things from execution to execution. But in general, the default is um, functions that we call have like an instantaneous life. They come to life. They get the parameters that we pass them. They do their work. They create whatever other variables that they want, and then those variables go away at the end of that invocation of the function. The next statement in main is a bare print, which produces a blank line. Python encounters another call to sing and control. It transfers to the sing function with the formal parameter Lucy. And I think he meant the actual parameter Lucy. Because if we look at the calling code, this is the parameter. This Lucy is an actual parameter. Now, we set the formal parameter person to Lucy. And that's what probably meant to talk about. The body of sing is executed for Lucy, and its three side trips to happy, and control returns to main. And then we come back there. Okay. So what happens now? Well, when main is done, the program's done. One thing not addressed in this example was multiple parameters, okay, because we're only passing one at a time. In this case, the formal and actual parameters are matched up based on their position. For example, the first actual parameter is assigned to the first formal parameter. The second actual parameter is assigned to the second formal parameter. So when you need to pass in more than one parameter, they're matched up by their position. And he gives an example that has to do with the code from chapter 4, and I'm not going to spend time on that. Okay. There'll be more on passing multiple parameters and matching them up by position in my supplemental material. Okay, now let's talk about functions that return values. Okay, passing parameters provides a mechanism for initializing the variables in a function. Parameters act as inputs to a function. We can call a function many times and get different results by changing the actual parameters that we pass to it. We've already seen numerous examples of functions that return value to the caller. And this is something that we didn't do in my class. But I think we did show the square root um, and we get a value back. Okay. Here's a very simple function that we're hand coding in our own program called square. And the formal parameter is x. Maybe not a good parameter name, except that this is kind of algebra, right? And x is a good algebra name. So uh, we pass in x and then we return x times x. When Python encounters a return, it exits the function and returns control to the point where the function was called. In addition, the values provided in the return statement are sent back to the caller as an expression result. So if we call square and we pass 3, what's the value that comes back? 9. If we say we want to print the square of 4, then we print 16. If we set x equal to 5 and y equal to the square of x and we print y, well, y is equal to 25. And we say that we want to print the square of x plus the square of 3. So the square of x, x is still equal to 5, so that's 25 plus the square of 3 is 9, we're going to get 34. We can use the square function to write a routine to calculate the distance between 2 points. This uses the Pythagorean theorem. This is essentially a little algebra with geometry in which we can calculate the distance between 2 points. Functions that return values, some more facts. The order of the function definitions in the program is not important. And I showed you that before when I was refactoring this Sing program. We just have to make sure a function is defined before the program actually tries to run it. Okay? And the thing to remember here, let's look at our happy refactored program. When does the program run? Well, when we call main. So as long as all the functions are defined before we do the call to main, then it doesn't matter what order they're in, okay, as far as the mechanics of Python are concerned. Now, good coding practice would say that we put these in kind of a hierarchical order. You know, we have functions who call functions, and some of the subfunctions call sub-subfunctions, and they might call functions. And you could kind of draw a chart that would look like an organization chart about who reports to whom. Okay, try to put them in that kind of order. If you looked at the org chart and then you listed out things top to bottom, left to right, that would be the order in which I think is a good order to put these in. Okay. Now it doesn't want to move. Come on. There we go. Since our call to main does not usually happen until every last line of the module, until the very last line, not the every last line, the very last line of the module, all the functions will be defined before the program starts running. So we don't have to worry about that provided that we do our call to main as the very last thing. And that's the practice we're following. Okay. So we just want to put them, we want to arrange the functions in a hierarchical order. That's what we do in my class with main at the top. Why? Well, it makes it easy for humans to read it and find things. Does the computer, does the Python infrastructure really care? It does not. Sometimes the function needs to return more than one value. To do this, simply list more than one expression in the return statement. Now, I'm going to show you how this works. I'm going to explain how this works, and I'm going to go on and explain why this is a bad example, and I'll show you better examples in my supplementary material. So he defines a function called sumDiff. Now, the name of the function is not in appropriate Python snake case, so that would need to be fixed. And he's passing in x and y, and we're just assuming that they're arbitrary number values, okay? So then he calculates the sum as x plus y. He calculates the diff, by which he probably means the difference, as x minus y, and then he returns them both, sum, comma, diff. Okay, no parens around this, just sum, comma, diff. Okay, all right. So this is a good example of a function that generated two different results that it wanted to communicate back to the calling code, and it did that by passing back two values. Okay. When calling this function, use simultaneous assignment. Okay. Well, what do we mean? Well, he's really talking about the code right here. Let's see if I can highlight it. Okay. Sometimes I try to highlight things and it works. Yeah, I'm trying to highlight right here. Okay, and what he's trying to say is, if you're going to call sumDiff and pass in two values, you're going to get two values back. Now, we're going to learn, well, we should know, and I'll talk about it more explicitly in my supplemental material, what really comes back from a function that returns more than one value is a tuple. So what does this left side do? Okay, it just unpacks the tuple. Okay, so typically when we call a function that returns more than one value, we just unpack the tuple that comes back so that we have these individual values and they're kind of properly named. Okay. Now, I just want to point out, I just want to go back to sumDiff and say that, oh, that was a really bad thing. So, I apologize for this. I didn't do that. I touched one key and it went all the way back. Functions that return values. Let's go back to sumDiff. Here it is. Okay, so one of the things that I'm going to emphasize in the supplementary material for Chapter 6, and then when we get on to Chapter 9, when we talk about program design, is when we design functions, there are two general principles that we want to keep in mind. We want to maximize a thing called cohesion, and we want to minimize a thing called coupling. And cohesion and coupling are two computer science terms that have been, hanging around. These principles have been hanging around for about 50 years, so a long time. And most thoughtful programming people would agree that they're still good principles. Well, what does it mean to have high cohesion? Well, cohesion is the extent to which all the code in a particular code unit is all about the same thing. Okay. What does it mean to have low coupling? Well, we'll probably be focusing on that more in chapter 9. It has to do with functions should know as little about the internals of each other as possible. Okay. The only thing that they should know are how do you call it and what do you expect to get back. The combination of those things is called the interface of the function. How do you call it? What do you get back? Okay. So what's wrong with SUMDIF? Well, it's not all about the same thing. It has very low cohesion. At getting the sum and getting the difference, they bear a mathematical relationship to each other. They certainly do. Okay. Are they the same thing? Are they part of the same thing? Only in a mathematician's mind are they part of the same thing. Okay. In a programmer mind, which I'm trying to help you develop, this is a poor choice of an example of a function that returns more than one value, because it returns more than one value by doing two distinct things. Okay, so I'm not going to criticize it any further, but in the supplementary material and in chapter 9, I'll be showing you other examples of functions that return more than one value that are much more appropriately designed. Okay. Now, one gotcha in return values for functions. All Python functions return a value whether they have an explicit return statement or not. So you can think of functions that don't have a return statement in them as having an implicit return statement at the bottom of the code. So when you go through the sequence and you get to the bottom, it does a return. What does it return? Well, there's a special value. It's actually a type called none. Somewhere in Python, there's a none class, and it means no value. Okay. So one common problem that you have when you're coding and testing a function that is expected to return a value is you forget to code the return, and then you're testing your program and all of a sudden you see this value none. As soon as you see that, you know that what has happened is in your function that was supposed to return a value, you didn't explicitly do that, and so you got an implicit return of none at the end. And when you're seeing none values go floating around the program that you're testing, you'll know that somewhere in it you forgot to explicitly return the value that you were expecting to return. And that's what this slide number 48 says. Functions that modify parameters. Okay, so you might think, well, do I have to return a value? Couldn't I just modify the parameter that I was passed? Okay, and then I don't have to worry about returning a value. I'll just change the value as it's seen in the calling code. And the answer to this, which we're going to illustrate, is in most cases that doesn't work. Okay, there are just a few cases in which it will work, and we'll show you that too. Okay, so return values are the main way to send information from a function back to the caller. That's the main approach, okay? Sometimes we can communicate back to the caller by making changes to the function parameters. This is the exception to the general rule that you can't do that. Understanding when and how this is possible requires the mastery of some subtle details about how assignment works and the relationship between actual and formal parameters. So we're going to explain this in detail. And the first thing we're going to show you is how, in general, this won't work. Okay. And the second thing we're going to show you is in a few special cases, it will work. Okay. Suppose you're writing a program that manages bank accounts. One function we would need to do is to accumulate interest on the account. Let's look at a first cut at the function. So we create a function called add interest. Again, this doesn't have a proper snake case Python name. We pass it the balance and the rate. And then we say that the new balance, again, not snake case, equals the balance times 1 plus the rate. The rate would be a fractional value like 0.05 for 5%. And then we say that the balance it gets assigned the new balance. So what we're trying to do is to communicate the answer back by changing the value of the formal parameter. Wouldn't that be nice? Well, it turns out that doesn't work. Okay? So now we're going to test it. Okay? So we're testing this. I don't know why we don't call this main, but we set the amount to 1,000. We set the range to 0.05. We call add interest, and then we print amount, and we think that, oh, we're going to get 1,050, right? No, we don't. It's still 1,000. Okay, so I have a version of this that I'd just like to show. I took the code for add interest 1, which is what this was called in the code that accompanies the chapter, and I refactored it. So I've got an add interest 1 refactored. So I created a doc string, demonstrate that parameters that are immutable types, like ints and floats, cannot be changed in a called function. Okay, so let's look. We're going to run this, and we get 1,000. So what did I change here? Well, I changed the main. I changed the function that he was calling a test. I changed it to main. That's our good practice. I changed the name of the function so that it's a proper snake case add interest. But apart from that, I didn't change too much. And I got the same answers. Okay? So if what you're passing is an immutable object, if it's an int, or if it's a float, or if it's a string, you might think you could write a code to change the value so it could be seen in the calling code, but the answer is it doesn't work. And it has to do with the immutability of that object. Okay? So let's follow along a little bit more with the discussion. The first 2 lines of the test function, which I turned into main, create 2 local variables called amount and rate, which are given initial values of 1,000 and 0.05. Control then transfers to add interest. The formal parameters are balance and rate. They're assigned the values of the actual parameters, amount and rate. Even though rate appears in both, they're separate variables because of the scope rules. Okay, And so this rate up here, okay. Oh, I'm sorry, the calling code came second. I hate it when people do that. So the rate that is the actual parameter in the calling code, and the rate that's the formal parameter in the called code. This is just coincidence, okay? These are not the same, uh, they are not the same variable, okay? Now, when we get to the called code, okay, the um, the value from rate in the called code is copied um, to the formal parameter rate. Uh, I'm sorry, the value of rate in the calling code is copied to uh, rate in the called code. But that would work if this was called another name. What I typically do is when I write the called code, I usually make the formal parameter names slightly different. So I'll call it A underscore rate or the underscore rate. And I do it to emphasize to students that um, these are not the same thing. They may accidentally have the same name, but they're not the same thing. The assignment of the parameters causes the variables balance and rate and net interest to refer to the values in the actual parameters. So how do they refer to it? Well, here's what happens. When we say that the value is copied to the formal parameter, well, the formal parameter in the call code just after the copy, it points to or refers to the same value object. Now, this might seem very promising. It's like, wow, Kevin, it's pointing to the same object. Then we can get it to change. Then we can change it. That's not how things really work in an object-oriented language like Python. We never change this value object, this int value object 1000. What happens? It looks in the code, when we see code like this, it looks like we change it, but we don't change it. It looks like we change it. What we get is a new object. So with these immutable types like int and float and string, it might look like we're changing the value of this object, but we're not. We're creating a new object. Okay? And that's the reason why it doesn't work. Okay? Because I'm going to go down, and here's we're going to see what happens. In the called code, I'm so sorry about this. I don't know why that jumps around. In the called code, we can see that we've got the line that assigns, I'm so sorry, assigns the new balance to balance. Okay? But what happens when we assign the new balance to balance? That formal parameter balance in the called code, now it's pointing to a whole new object. Okay? What about amount in the calling code? Have we made that point to a whole new object? We have not. So that's why when we get back into the calling code and we print amount, it's still 1000. So the result of this is that the formal parameters of a function only receive the values of the actual parameters. The function does not have access to the variable that holds the actual parameter in the calling code. That's why Python is said to pass all parameters by value. So we just back up, the problem is that when we change the value and the called code, okay, we're not replacing some value. We are creating a whole new value object, and now only amount is pointing to the 1000 value object. So in called code, you can't change the value of a parameter that's been passed to you and have that be seen in the calling code. As long as it's an immutable object, the calling code's never going to see that change. Okay? It's disappointing to many people, but that's the way it works. Now, in some other programming languages, something like this would work. Okay? But not in Python. Now, there's an exception to this not working, and that's when you're passing in a mutable object. Okay, well, what are the mutable types that we've learned about so far? Just list, okay? So if we passed in a list, and then the called code manipulated the values in the list, we're going to see that the calling codes could see those revised values. Okay? So let's see what we can do. So here we've got I think this is the original version. Yeah, that's the one that didn't work. Okay? So let's look at the new version. This is a program that came with the chapter Add Interest 3. Okay, so let me pull over the real code in PyCharm, and we see Add Interest 3. And of course, I have a refactored version, so we can look at that. And of course, it's got a doc string programmed to illustrate modification of list items in a called function. Okay, so if the data that we have is in a list, because lists are mutable, if we pass the list, amounts as a list, okay, we pass amounts, okay, the called function here uses a different name. Now, I think this is a good practice. Here it's amounts, here it's balances, that's fine. One thing that I often do is, rather than use the same name, even if I can't think of another name, or I think it's going to be confusing to introduce another term, if the calling code has the variable called amounts, in the called code, I'll just call it the underscore amounts, or this amounts, or something like this. Okay, so here what's happening is we've got 4 amounts in the list. These are all ints. The rate is still 0.05. We call add interest. I've cleaned up the name. We pass amounts and rate, and then we print amounts. Okay, and we're going to get the higher values. And then in the called code, add interest, we're being passed the balances and the rate. So we say for I in range length balances, okay, it would have been just as easy to say for balance in balances, but this is the way he wrote the code. We say, oh, I see. No, we don't want to do that. There is a problem when you're trying to update values in a list, that the typical for in doesn't work. So if we said for balance and balances, and then we tried to update the name balance, that won't do it. So this is why we have this code. So we're referring to the one that we want to update as balances index I, and we're assigning balances index I times 1 plus the rate. We should probably put a space around that plus so it can be read a little better. Okay, that's going to work. Okay, so now we're going to run. And you can see we're up to 1,050, 2310, 840, 378. So that's a scene in the calling code. And why did that work now? Well, because the value, the value object is a list, and we can change the values that the list is pointing to, and we can still see them in the called code. And now we're going to see a kind of a play-by-play explanation of how that works. Remember the original code had these values. Okay, those were the original values. The program returns updated values. What happened? Python passes the parameters by value, but it looks like amounts has been changed. That's because it's a list and it's mutable. And that's the code. And here's what's happening with the values. Okay, so when we come over here to add interest, okay, we're going to match up balances with amounts and rate with rate. Okay, and what happens? Well, then the rate in the called code is pointing to the same value as rate, and the balances in the called code is pointing to the same value object as amounts. That's a list. That's a mutable object. And here are their initial values. Okay. Now, then we execute the code and the called code. We update these, and here's what happens. This list object is now pointing to the new values, and these old values, we don't know what's going to happen to them. If there's nothing else pointing to these, they're going to become candidates for garbage collection. Okay. So they'll probably be garbage collected pretty soon. But what's interesting is the called code is referencing or pointing to this list object, and the calling code is also pointing to the list object. So when we get back to the calling code, we can actually see the new values. And this just has to do with the fact that what we passed is a mutable object. It's a list. So far, that's the only mutable type that we know. Now, we'll learn when we get to chapter 11 that dictionaries are mutable objects as well. So you could do this with a dictionary too. But so far, the things that we've learned about and we're using only lists. So far, functions have been used as a mechanism for reducing code duplication. That's that dry principle, don't repeat yourself, which I keep repeating, oddly enough. Another reason to use functions is to make your programs more modular, okay? Right. As the algorithms that you design get increasingly complex, it gets more and more difficult to make sense out of the programs. Okay, so if we put all of our code into main, it gets harder to write the code if we don't factor out code into functions. Um, and it gets very hard to read and to modify code. So, and that's just big pieces of code are hard to work with. One way to deal with this complexity is to break an algorithm down into smaller sub programs, which make sense on their own. This is a topic that we're going to discuss when we get to chapter 9. And in some of the supplementary material that I provide, I'll be toying with it even before we get to chapter 9. And that is the end of the chapter, I think. It is. So, having reached the end of the chapter, I'm going to say bye until next time. Bye bye.